Okay, welcome to video 2 for the Advanced Drivetrain Unit Notes. Now, to start this one off, I want to talk about how to calculate the mechanical advantage needed for a lifting system. Now, to help us, we need to go back to the definition for mechanical advantage. So, to do that, it's going to be the output torque equals the input torque times your mechanical advantage. So let's take a look at this example here. Here we have a 30 Newton object placed on the end of a long arm that's 0.5 meters long, and we don't know what gear ratio we would need. Well, that should be pretty easy to find. First off, we need to find out what the output torque is. And remember that torque is defined as force times lever arm distance times sine of the angle between. And we're going to say theta is 90, that way sine of 90 equals 1, and it just goes away. So the output torque will equal 30 newtons times 0.5 meters, which equals 15 newton meters. Well, for a 393 motor, the input torque is 1.67 newton meters. So the mechanical advantage needed would be the output torque divided by the input torque, which would be 15 newton meters divided by 1.67 newton meters, and that equals 8.98. Yeah, why not? We'll just round it up to 9. So we would need a mechanical advantage of 9. And looking through the VEX gears, I think the best way to get that would be to use a 12-tooth gear meshed with an 84, and then in compound a 36 to a 60. That mechanical advantage would be 84 over 12 times 60 over 36, which would equal right around 11. I think it's like a 11.7. So that would give us plenty of mechanical advantage with some extra to spare. Now this next one, this is a scissor lift. And scissor lifts are a little more complex. I had to do some digging around on the internet, but I found this formula to calculate the torque needed for a scissor lift. So that's what I found to calculate the torque needed to move a scissor lift. So let's look at each part of this formula by itself. So the F represents the weight of the scissor lift plus what you're trying to lift. The D represents the length of the levels for scissors. So that's like the length of the bar plus how many levels you have. And what I mean by levels, if we come up to this picture right here, on this one, I'm counting 1, 2, 3, 4, 5, 6. So 6 levels. The theta, the angle, should be the angle between the scissor and the ground when compact. So if I were to draw this out, so let's say this is the wheels on the robot, and we have our first bar right here. Let's say that this is when it's compacted. That would be theta. So that's when it's all the way down, which kind of explains, when this comes all the way down, uh, this theta becomes 0, and cosine of 0 equals 1. So if you think about it, when this is compacted all the way down, you have the maximum amount of torque, or you need the maximum amount of torque just to move the thing. But if theta is something less than, or something greater than 0, it requires a little less torque, because something, cosine of something that's non-zero is always less than 1. All right, let's moving on. Turning torque needed to overcome scrub. We talked about scrub last year. This is the resistance to turn for zero-turn systems. It happens because of friction between the floor and the wheels on a machine. When you look at a road surface, if you see damage after a construction crew has been through, that's usually because of the scrub between the tank tread on like bulldozers and backhoes. That tank tread, it has a lot of scrub in it, and that can do a lot of damage to the roads. Now, if you design your robot with a long wheelbase, it's going to require more, or it's going to have more turning scrub than a wider wheelbase. And let's talk about why that is. So here's our diagram, and let's say I want this to make a counterclockwise turn. That means that each wheel on the right side would need to apply a force going this direction, and these wheels would need to apply a force going that direction. So looking at that, we can figure out how much torque it is in the turn. So remember that torque is force times lever arm distance times sine of theta. So we need to have these to be perpendicular. So for this case, this distance x is perpendicular to the force. So the turning torque would equal F times x plus F times x plus F times x plus F times x. So basically, this turning torque would equal 4 times F times x. And if you remember, for the wheel, the torque on this wheel, this force would equal the torque on the wheel divided by the wheel's radius. So the total amount of torque needed to turn equals 4 times the torque at the wheel divided by the radius of the wheel. And when we take a look at the motors and the gearing, we can figure out how much torque is at the wheel. So that is how much torque is needed to turn it. Now there's scrub that fights it. So as this turns, we have friction, and friction opposes sliding. So here we would have some friction pulling in this way, and some friction pulling out in that way. And this is all kinetic friction because it is sliding. And that adds up as well. So the torque for the scrub equals friction times y plus friction times y. So basically, this turning scrub equals 4 times the kinetic friction times that distance y. And now this distance x, that distance y, that's all based off of the geometry of your own robot. So you can actually measure that and calculate this. Now, friction is the coefficient times the normal force. And the normal force is going to be the same as how much the robot weighs, since we're dealing with a flat surface. So this friction is going to be coefficient times m times g. So the turning scrub equals 4 mg mu times y. Now, as long as the torque you have to turn is greater than the torque that you have scrubbed, the robot will be able to make a turn. This is still a problem, though. We still want to eliminate the scrub as much as we can. So that's where we have the omnidirectional wheels. The use of omnidirectional wheels will eliminate scrub altogether. But what happens is, if you still have some high direction or high traction wheels, the turning point always goes towards the high traction wheels. So this robot will turn very easily on its backside. The pivot point has been moved forward. Well, that finishes the notes for this unit. Ciao.